Hello everyone. We will start our session. Yeah, sorry. Hello everyone. We will start a session soon. Let's wait for students to arrive. वो chemical treatment. We will start the class. Just 1 minute. हाँ start. हाँ हाँ. Hello. हाँ हाँ. ओ ठीक है. लेकिन वो इशू नहीं है. इशू ये है कि टेम्परेचर 104 के ऊपर नहीं आ रहा है. हाँ 121 हमारा टेम्परेचर रीच करना. ठीक है. Okay, so we will start the session. Hello Satish. Uh, let me share. One minute. Okay. So this week it's mostly about spectral representation of whatever signals you have, and its application and estimation theory. We will first discuss the assignment, and once we are done with assignment, we can discuss if any doubts are there. Uh, Before that, let's just recap what's there in that in the week. So spectral, we refer to the frequency actually. That at what frequency are these random processes acting? Is it uh, periodic? Even a non-periodic signal can also be converted into different frequencies. There could be infinite frequencies, which can result into a random signal, which is non-periodic in nature, but still they are a frequency. So let's say h is our impulse response of the random process, and frequency response function is your h for a frequency of w or omega. Let's say we have this spectral density uh, that decreases with frequency. That what at different the for any signal that we have, what are the density of the frequencies? The main reason that we study this is to have periodic phenomena in both all, I mean, natural, man made, all these processes. Is there some stochasticity or not? Or it is predictable, non deterministic? That is what our main question is. Spectral analysis will automatically come with harmonic processes. Harmonics are related to always frequency and periodicity. So harmonic analysis is a lot of time used. And for example, any harmonic process can be any discrete time stationary process which has a period np and follows this, that the estimation, the expected value, the mean value between the period, after a certain period of time or period of space, you the expected value and the initial value would be the difference would be zero. We have Fourier analysis is obviously used a lot of times in harmonic analysis. I mean harmonic processes that we have seen earlier also. And ACVFs has their Fourier series expansions. So that is what we will see most of the time. And spectral distribution function gamma is given here. Spectral factorization is a very important process because this will be the main process to help in finding out your each and every frequency. And this is a predicted model base, not exact, and all these model base comes from your data. Okay, let's start. Consider fluid level measurement example given in the class. Suppose we change the assumed model to be this. Earlier it was uh, only one constant. Now it has this, which has a normal distributed over zero with standard deviation of sigma e, where C1, C2, and sigma e are unknowns. Suppose the least square method is used for estimating these unknowns from observation. Which one of the following statements is or are true? Since if you take this signal and take the mean of it, you can say C1. So C1 can be either C1 or C2. Any one of them can be uniquely estimated, but not other. And but that depends upon what coefficient it is of. Ek, because of its random behavior, we have to assume that its estimation is zero. Therefore, C2 cannot be estimated. Only C1 can be estimated. And because of the normal process, its estimation would be C1 estimation would be zero. So C1 can be estimated uniquely, but not C2. Given a single observation y of an exponential white noise process with PDF, this is a Poisson sort of PDF, and a log likelihood function L, where theta is equals to gamma for all y, is it's very simple. You have to just use if this is theta equals to gamma, this function, it's very easily given already in the examples done by sir. So its answer will be this d log lambda minus lambda y equal to 0. If uh, not equal to 0, that is the probability. Suppose we redefine the parameter theta for the problem in question 2 as theta equals to 1 by lambda. Typically, in when we convert from one parameter, uh, in these cases, it's mostly Poisson when it convert. to 1 by lambda, it becomes exponential. So the value of the Fisher information of theta contained in n observation of the exponential white noise process is very simple. C. Because for a theta here above, it would be n theta lambda square. But if your lambda is, I mean, 1 theta is 1 by lambda, then you have to write n by theta square. A constant signal for unknown amplitude A is observed by two different but independent sensors whose variance are known to be sigma square and 4 sigma square respectively. Suppose a total of n equals to n1 plus n2 observations, n1 and n2 from sensor 1 and sensor 2 respectively are obtained. Given that n1 and n2 are greater than or equal to 0, choose n1 and n2 such that Fisher form information about A in the appended data is maximum. So in order to maximize, you have to choose this thing. Just 1 second. A constant signal of unknown amplitude A is observed by two different but independent sensors whose sigma and sigma square, 4 sigma square respectively. So N1 has to be chosen in such a way, N equals to N1 plus N2, and they are these, uh, the number of observations that one has to do is such that our information, the Fisher information is maximized. Given that your n1 and n2 are greater than 1, greater than 2. Since you have to write it as a function of n, because n1 plus n2 that remains constant, you have only certain amount of observations you can take. Suppose greater than 2, you can take 1 as 2, and that is the minimum information that is required, and rest can be just minus of that. So you can actually write n1 equals to n minus 2 and n2 equals to 2. But since you have sigma square and 4 sigma square, the variance is minimum in case of n1. So it is better to have maximum observation in n1. Therefore, if n is greater than 2, which is obviously because both n1 and n2 are greater than or equal to 2, it is better to have observations in n1 rather than n2. So you can minimize observations with higher variance, having n2 equals to 2 and n1 equals to n minus n2. N minus n1 minus 2. This one. For a periodic random process with np equals to 5, which of the following statements are correct? Since the period time is for a periodic, see it's periodic in nature, so estimated between your this two, that was the main first function slide, first has to be correct. Similarly, when you're talking about uh, variance, sigma VV. Since 15 itself is a multiple of NP, the variance itself has to come back to its original position. And variance of 10, I mean, so, see, you started with something uh, that is, you just put L equal to 0, you will get the same thing. 10 is again a period, I mean, multiple of 5, which is NP, the periodic time. So, answer is all the above. Given below is the spectral density. If it had been anything, let's say 7, then any this would not have hold true. Okay, let's continue. Given below is the spectral density function gamma VV with omega as the frequency of a stationary process Vk. Which of the following is an appropriate representation of Vk with sigma square equals to 1? What's the first thing that we have to see? First thing is to see the periodicity. It's 2 omega. So your options out of these four, automatically these one go away. You're left with these two. Because it's cos, the Q operator would have minus here. Sorry, Q operator would not change it. It would be whatever sign here. That's plus. So it's just a way, a trick sort of to understand. But if one has to do, one can obviously do the all processes to normalize it with sigma square equals to 1. For the spectral density function of a stationary process Vk, given in question 6, the PACF of Vk at lag L equals to 2 is, since it's lag, it will be negative, so it's minus 0.9. Uh, Here you can see minus of minus this thing, L minus L will be here, so it's minus 0.9. Which of the following best represents the filtering characteristics of the process Vk in question 6? Now, in question 6, we have this here. First thing that you have to see is sigma square equals to 1. Which do you think is sigma square equals to 1? This does not have sigma square equals to 1, multimodal. This does not, this does not have. Your first answer itself, first thing is only given here. Rather than it had been something like very spread out. So there are peaks, but they are not given properly. This is your answer. Generate a signal realization consists of n equals to 100 observations for the given MA process and compute the sample mean. Repeating this process about 10,000 times, the variability of the sample mean is approximately. Now, this is something you have to do in your R. You will get this value 0.02. Let's move to the next question. Which of the following spectral density qualitatively correspond to that of a MA process? C. Any MA process would not have these bumps. It would be so, no two maximas are there. So first is gone. You can see from the answers itself, these are two processes monotonically increasing and with a standard deviation, big standard deviation. That's the answer. Uh, Actually, this will come mostly with the help of more of experience for MA process. If anyone has any doubt, they can ask. If there are no doubts, we will end the session at 7 o'clock. In case anyone has any doubt, they can ask. If not, let's end the session at 7. Estimation theory is also very important, which will help. This is basically now all the basics has been done. Estimation theory is the epitome of this course, and that we will see in future classes. Okay, let's end the session.